Yeah, good evening. Uh, we'll start today's lecture. Okay, so all of you can see my PPT, right? Please respond.
Yes,
Okay,
sir.
so yeah, so in the last class we have started a new chapter, that is pile foundations, and we have seen the importance of this pile foundation, and so just to motivate you the importance of this chapter, I have shown some applications of these pile foundations. Okay, so the major application is in the offshore structures and in marine structures. Okay, so but as well as even if your soil is poor in the on the onshore structures, you can go for the pile foundation. So as I told, yeah, most of our coastal region, coastal deposits are very soft in nature. Okay, so there you can't rely on the shallow foundations, right? So we have to you have to go for the deep foundations. Deep foundation. One of the example is pile foundations. So if you see these wharf structures or jetty structures, where your container ships or big ships will come and they will loading and unloading will take place. Where here these big cranes has to carry a lot of loads. Okay, so to support these kinds of heavy loads, we need a pile foundations. Okay, so this is one of the applications, and also I have shown you some pictures where, to give some glimpse of the applications of these pile foundations. Hmm. So these things we already covered, and also we started with uh, the classification of piles. Okay, so the classifications are based on the five categories. Okay, so first category is the classification based on the method of installation. Okay, so how you are going to install them. Okay, so for example, in that we will have driven piles, driven and cast in place piles, jacked piles, screwed piles, and board and cast in place piles. Okay, so this is most important. Okay, so board and cast in place piles, which are widely used in our normal conventional civil engineering structures. Like multi-story buildings, and they usually especially in India, almost around 90% of the piles will be board and cast in place piles. Okay, so driven piles, mostly it will be used in these offshore structures, offshore and marine structures. Okay, so those will be used in see, these driven piles will be used in these offshore applications. Okay, but onshore applications, it's mostly the board and the cast in place piles. And the rest of the other piles are they have will be used in only some specific applications. So majority will be this one, driven, and this one, board and cast in place piles. And second type of classification is based on the load carrying mechanism. Okay, so like if the entire Q load, if the entire load is taken by, this is the pile, if the entire Q load is taken by the end bearing. Okay, then those kinds of piles are called as end bearing piles. Okay, suppose if this Q is entirely taken care by your skin friction, uh, then those piles are called as frictional piles. Hmm? And third type is combined. It is a combination of both. Okay, so part of Q is taken care by skin friction, and part of Q is taken. can nearby the end bearing. Okay, so those types are called as combined end bearing. Oh my god, I think some connection was lost, I think, right? Just now I saw your message on the WhatsApp. When the connection was lost? Yes. I don't know what was the problem. Hmm? Just now I got a message in the Google in this WhatsApp. You left the meeting. Okay, so I not left the meeting. Okay, so I was keep on uh, recording, but I think we have lost the connection somewhere. Mm, anyway, I will start with the beginning. Mm, okay, so are you able to see the screen now?
Yes, sir.
Okay, so I think we lost the connection in between. Okay, so no issue. I will repeat those things. Okay, so we were discussing about the load carrying capacity of pile. Okay, so we have two methods to calculate the load carrying capacity. One is called a static approach, and another one is called as a dynamic approach. Okay, so in the static approach, first, what will happen? These all after once you calculate the load carrying capacity, either maybe a static approach or maybe a dynamic approach. But in reality, what will happen in the field? You have to test certain piles in the field. Okay, so those are called your pile capacity or pile load carrying capacity of the pile. Those are called as these field tests. Okay, so in both approaches, it is necessary to confirm the pile capacity by carrying out the actual pile load test. Okay, so suppose if you are constructing some building here and you already installed some piles. Okay, so here like always you will not install a single pile. Most in general cases. Okay, so always you will install the piles in a group. Suppose we have a one group here and we have another group here and we have another group here. Okay, so what will happen? You have to choose certain piles randomly. You have to choose certain piles and you have to apply you have to apply the loads on these piles. Okay, until again in that also the two categories are there. Okay, so in detail I will talk about those tests in the coming slides. Okay, maybe after third or fourth hour, I think we'll once we come to that pile load testing, there we'll discuss in detail. Okay, so irrespective of method you used, you have to cross check them in the field. Okay, so first we'll discuss about the static approach. So how we will calculate the load carrying capacity with the help of the static approach. So yeah, so the static approach will use this solid mechanics concepts. Okay, so whatever this Q is there, no, this Q is carried by part of this Q is carried by your base. Okay, that is your base resistance, and part of this Q is carried by your shaft resistance. Okay, so this is QS. Okay, so this Q ultimate is nothing but your base resistance, ultimate base resistance plus your shaft resistance, ultimate shaft resistance, or even you can call it as a skin friction also. Okay, so this QS is called as skin friction or shaft resistance, and this QB is called as base resistance. So this total Q is shared among these two. Okay, so one is the base resistance and another one is the shaft resistance or a skin friction. So you have to add up both. So your Q ultimate is nothing but QBU plus QSU. So what is QBU? What is QBU? QBU is nothing but your base ultimate base resistance intensity into the base cross sectional area. Okay, so this is the base cross sectional area, and this QBU is nothing but ultimate bearing capacity or unit base resistance. Okay, so this QBU is equal to capital QBU is equal to small QBU into AB. AB is nothing but your cross section area. Okay, so if you have a circular pile, then cross sectional area will be usually pi by 4 into d square. Okay, if you have a square, then side square will be your cross section area of your base. Okay, then what is QSU? QSU is nothing but your shaft resistance. This one, shaft resistance or skin friction. So it is equal to summation of your QSUI, small QSUI into surface area. Okay, so why I am taking a summation here? Because we will be having a different soil layers. We'll be having different soil layers here, right? So this is maybe soil 1, 2, 3. Okay, so here we have 3 soil profiles. Okay, so each soil profile will have a different properties. Okay, so that's why you have to first that's why I'm taking the summation here. Okay, so you have to add the skin friction of this layer and this layer and this layer. Okay? That's why this summation sign is there. Okay, it's simply I going from 1 to n. That is I is nothing but number of soil layers into Q small q SUI into ASI. Okay, what is this Q SUI? It is nothing but unit skin friction or shaft resistance. Okay, so what is the ASI? ASI is nothing but your pile shaft area. Suppose if you have a circular, then it will be pi d into L. Okay, that will be your surface area. Okay, so now we will see how to calculate this these parameters in different types of soil. Suppose if you have a sandy type of soil, then how we can calculate, and and if you have a clay type of soil, then how you can calculate these your base resistance as well as your shaft resistance. So just recall from your shallow foundations what we have studied in shallow foundation. If you remember your ultimate load carrying capacity of your shallow foundations, it is CNC plus QNQ plus 0.5 gamma B in gamma. Okay, so this first term is contributed by what? The cohesion term of your soil. Okay, and this second term is contributed by the surcharge, that is the soil present above the footing, and this third term, it is contributed by this soil present below the footing. Okay, so whatever this pile is there, no pile base resistance. Okay, so this pile base resistance is it is just resembles your shallow foundations. Okay, so like, but except for your width. Okay, so here width will be higher, but here pile will have a very small width here. Okay, but it is also failing by like same concept. Okay, let me draw here. So it will also form a small cone here, and then from this cone you will get a failure surface like this. Okay, but this whatever depth will be there, this will be very small because your pile dia is very small. Okay, so maybe like 300 mm or 400 mm pile diameter will be there, but whereas your shallow foundation width will be like half meter or 1 meter, 1.5 like 1.5 meter. So usually it will be a bigger size. So see, now we'll see in granular soil. In granular soil, how you can calculate your ultimate load carrying capacity. So first we'll discuss about the granular soil. Granular soil means what? Like sand. So how you can calculate? So what is Q ultimate? Q ultimate is nothing but it is a combination of base resistance plus the shaft resistance. So what is QBU? This QBU is equal to small, that is unit base resistance into the area. Sorry. So unit base resistance into base area. Okay. So how you can calculate this base resistance? This is base unit base resistance is nothing but, if you recall your shallow foundation, what was the formula? CNC plus QN Q plus 0.5 gamma B n gamma. Okay, so if you recall from then, suppose if you are having only sand, then this term will be 0. Okay, so you left with only QNQ plus 0.5 gamma B what? N gamma. Okay, so let me write here properly this one. So let me write here once again. So QU is equal to CNC plus QNQ plus 0.5 gamma B N gamma, right? So wait a minute, just I want to plug into my laptop. I think it's getting drained out. Okay. Give me a minute. Just I will put a charger. Yeah. Okay, so if you are dealing with only sand, what will happen? This term will be 0. Okay, so you left with QNQ plus 0.5 gamma B N gamma. Okay, so if you see that, the same format here. Okay, so instead of Q, I represent it with a sigma bar. Okay, so even you can write Q only. Okay, so it is not going to differ. Only the nomenclature, whatever this nomenclature I am using is a little bit different in piles. Okay, so as compared to your shallow foundation. Anyway, the sigma bar is nothing but water. It is the effective overburden pressure at the pile tip. And this NQ and N gamma are the bearing capacity factors. So these NQ and N gamma are the bearing capacity factors. It is little different from your shallow foundations, okay, because of different shape factor and different depth factors. Okay, so you can't take NQ N gamma from your 6403. So for this NQ N gamma 2911 I should use. Okay. So this QBU is this QBU. So this QBU is nothing but your shallow. If you remember the formula from your shallow foundations, the same formula here we are using. Okay, sigma bar into NQ plus 0.5 gamma D N gamma. Okay. So then once you multiply to this thing with the base area, then I will get the load. Okay, so this is the intensity, load intensity. If you multiply with the area, then I will get a load. So what is sigma bar here? Sigma bar is nothing but effect. It is the effective overburden pressure at the pile tip. And what is the NQ and N gamma? NQ and N gamma are bearing capacity factors different from shallow foundations because of a different failure surface and your different failure surface, and of course the depth factor also will play a role here. So that's why these NQ and N gamma are different than your shallow foundations. Then what is D here? What is D here? D is nothing but the diameter of the pile. Okay, so like what is the diameter of your pile? So this is my D. Then see one more thing you should remember here. Okay, so 0.5 gamma D. See, D is very small here. See, it will be like maybe 200 mm or 300 mm. So that as compared to this term, let me take a different color here. So as you compare to this term, 1 minute. If you compare to as compared to this term is very negligible. This term will be very negligible. Why it is negligible? Because my depth is very small here. Sorry, my diameter of the pile. Diameter of the pile is very small. That's why this term is going to be negligible as compared to the my first term. That's why this term can be neglected. Okay, so this term can be neglected. That's what I'm writing here. 0.5 gamma D N gamma is negligible compared to your sigma bar into NQ. Okay, so sigma bar into NQ, see the depth of the pile is very huge because this sigma bar is there. This sigma bar is what? Sigma bar is nothing but the overburden pressure. So this overburden pressure indirectly it depends on the depth of pile. Okay, so your depth of pile is very high as compared to the diameter of the pile. Okay, so that's why I'm neglecting this second term. Okay, so if I neglect that term, then what I will get? I'll get this term QBU is equal to sigma bar NQ into AB. Okay, so you erase this term. You don't consider this term. So then what I will get? Sigma bar NQ into AB. Okay, so this AB term is for entire thing. I think I should put a bracket here. I forgot to put a bracket here. Then this AB will be multiplication for entire thing. So finally, what you will get? Your ultimate base resistance is nothing but sigma bar into NQ into AB. This is your final base resistance of the pile. Okay, so QBU is equal to sigma bar into NQ into AB. So this NQ is there. This NQ is the bearing capacity factor, and it depends on the phi value. That is your angle of internal friction. So in IS 2911, we have a graph between a phi value and NQ value. Okay, so you can get the NQ value from that graph. Okay. So here you see this is the graph. So we will stick to IS 291. Different authors have given different curves here. Okay, so this curve is given by Terzaghi, Meyerhoff, Hansen. Different authors have given, but we will stick to IS 2911. What IS 2911 is telling. Okay, so for different phi value, we will get a NQ value. So which can be plugged into this equation, and then you can get the ultimate base resistance. So here I should have a bracket here. Okay. So this is about ultimate base resistance. Then what is the left thing? Okay, so this thing we have calculated. Now we have to calculate the shaft resistance. Till now what we calculated? We calculated only the base resistance. Okay. So next, how to calculate the shaft resistance? Okay, so to calculate the shaft resistance, we will use this formula. So QSU is nothing but the ultimate shaft resistance is equal to summation I equal to going from 1 to n, that is the number of layers, into your small q SUI into ASI. So ASI is nothing but surface area of the pile, and QSUI is nothing but the intensity. Okay, our unit resistance, unit shaft resistance you can call it. Okay, so that is your QSUI. So this QSUI, how you can calculate? See, this QSUI is nothing but it is a function of your QSUI is again function of your vertical load or overburden pressure. That's why you see the overburden pressure K times sigma AVI into tan delta. Okay, so what is the sigma AVI? Sigma AVI is nothing but your overburden pressure. Suppose here I have a different soil layers. Okay, so let me draw. This is layer 1 and this is my layer 2. Okay, so this is my layer 1. So in this layer I am calculating the shaft resistance. Okay, so this is like QS1, QS2 and QS3. Okay, so summation I should take this thing I have to add up, then only I will get a skin resistance or shaft resistance for the entire pile length. Suppose I'm calculating at this level. Okay, so what I have to do, I have to take it at the middle of the clay layer, okay, or middle of the soil layer, and at the middle of the soil layer I have to take the overburden pressure at this level. At this level, what is the overburden pressure? So that times, that is like your vertical stress. Okay, so if you multiply that with your earth coefficient, no, then what will happen? See, suppose if I take a small soil sample here, so what is your vertical stress here? The vertical stress is nothing but gamma times the length. Suppose this length is some L1. Gamma times L1 is my vertical stress. Then what is your horizontal stress? This horizontal stress is nothing but the K times your vertical stress. That is your earth pressure coefficient times the vertical stress will give me the horizontal stress. Okay, So that horizontal time stress times the tan delta. Okay, so this tan delta is nothing but it's the average effective overburden pressure for the sorry, this delta is the this delta is the this wall friction. That is wall friction. That means the friction between your pile and soil. Okay, so that is my delta. So it is just horizontal stress multiplied by your angle of wall friction. No? Tan of angle of wall friction will give me shaft resistance. Okay, so this is the formula. Understood how I got this formula? See, this is just it is also a function of your vertical effective stress. So first, what I will do, I will calculate the effective stress, vertical effective stress. Then I will multiply with my earth coefficient. I will multiply with that. Then in turn, that will be multiplied by your wall friction. Okay, or angle of wall friction we can call. How much is the angle of wall friction? Usually angle of wall friction will be two-third of your this friction angle for driven piles, or you can take equal to phi value for the bored piles. If you have a bored piles, then you can take it as a phi value equal to phi value, or if you have a driven pile, then two-third times of phi value you have to take. Okay. So why I am reducing here phi value? Two-third means what? I am reducing the phi value here. Why I am reducing here, and why I am taking full phi value here in the bored pile? Because bored piles, bored piles will disturb very small, very little disturbance will be there to the surrounding soil. Okay, so that's why full phi value I am taking here. So I am reducing two-third times because here because of driving the pile, whatever soil present surrounding the soil will be disturbed. That's why I am reducing phi value. Reduced phi value I am taking here. So that's why it's a two-third of phi value. Okay. So this is the method to calculate the shaft resistance. So any doubt here regarding these two calculation part? The first is we have to calculate the base resistance from this formula, and then we have to calculate the shaft resistance from this formula. Then combination of total Q is equal to your Q ultimate base resistance plus ultimate shaft resistance will give me the total Q. Understood? Okay. So these things we have till now we discussed for the granular type of soils. What if you have a clay type of soil? Okay, so for that we have another method called so static approach in cohesive soil. So in the cohesive soil, how you will calculate? Okay, so in the cohesive soil, Q ultimate is equal to base ultimate plus your shaft ultimate. Okay, so this base ultimate here, see if you recall from your base like from your shallow foundations. Okay, so CNC Q NQ plus 0.5 gamma B N gamma. Okay, so in the clay, these two terms will become 0 and only CNC will take. Okay, so that's why CNC into the base area plus summation I going from 1 to n alpha times your cohesion value into cross section area. So this is alpha times your cohesion value into cross section area. So that is in case of cohesion in cohesive soil, that is in clays. In clays, we will calculate your ultimate load carrying capacity of the pile from this formula. So coming back to my sand here. Okay, so once I get your total Q, so once I get the total Q, then here some values they given. Okay, so like how you can get the delta value. Okay, so whatever delta we are talking now here. So usually IS code will tell you these two, like 2/3 of 5 value, or 5 or you can take equal to 5 value for board files in the IS code. But in some other like brooms, they will tell you how to choose your 5 value depending on the material, like your pile material, and also your value of K for the corresponding pile material, how much K I should take. Okay, so like your K is there, no, here. That K is nothing but our coefficient of earth pressure. Okay, so this value of K, if you are using steel, then you can take 0.5 to 1, then concrete 1 to 2, then timber 1.5 to 4 you can take. So IS 291 part 1 1970 recommend the delta value is equal to 5 for driven piles. Okay, in loose to medium sand, the recommended value of K is between 1 to 3. Okay, so in the next class I will open the 2911 and I will show you what are these where you can find these, all the formula and all these guidelines. Okay. And in this sand, we will have one very important concept called critical depth. So this critical depth, see what will happen. What happened was this Vesic is experimentally they conducted some. They have done some experiments in the laboratory, and then they come to know that whatever your see, both your skin friction and your base resistance. It is a function of what? It is a function of your vertical effective stress. Okay, so this vertical effective stress, what will happen usually? The vertical effective stress, it will keep on increasing as you go deeper and deeper. But experimentally, what they found was, see, this effective stress is this effective stress will keep on increase as you go deeper into the soil. That is your sigma. But from experiment they found out that that will not happen. Okay, so this sigma will not increase all along the pile depth. So it will increase only up to certain critical depth. Later on, it will become constant. Okay, you see this constant value. Sigma V will not increase as you go deeper and deeper. Okay, so of course it will start increase for certain depth. After reaching certain depth, then it will become a constant. So that depth is called as DC. That depth is called as DC. Okay, so why this phenomenon will occur? This phenomenon will occur due to your arching effect. Okay? So due to this arching effect, what will happen? The increase in vertical stress will not increase all along this depth. So it will increase only up to certain depth. Then it will become constant. So usually the critical depth will be taken as 15 times the diameter of the pile if your phi value is less than 30 degree, and usually it can or you can take your critical depth, that is the depth up to which the stress will keep on increasing. Okay, so that can be taken as if for a soil is having phi value greater than 40 degree, then your critical depth will be 20 times the diameter of your pile. Okay, so this is the diameter of pile. Okay. So this critical depth concept is this will happen only in sand, not in clay. So this will happen only in the sand. So these two are the final your formulas to calculate the load bearing or load carrying capacity of the pile. Okay, so QU is nothing but base resistance plus shaft resistance, and then this QBU, how you can write? You can this is nothing but sigma bar, that is your vertical stress, times NQ value multiplied by the base area. And how you can write your QS value? QS is nothing but your vertical stress times your lateral earth coefficient into tan of delta. Okay, so that will give me a small QSU. If you multiply this small QSU with the help of your surface area, cross surface area, then I will get a QSU. Okay, so this is in sand. Okay, it is in sand. So if you have a clay, then this formula you should use. If you have a clay. So here you see what is QU, ultimate load carrying capacity of the pile, is equal to base ultimate plus shaft ultimate. Okay. So what is the ultimate? QU is equal to what is the what is your capital QBU? Capital QBU is nothing but the area of your base, and this together will be your small QBU. Okay. So small QBU is nothing but your cohesion times the NC. Okay. Plus summation I going from 1 to n alpha I into CUI into ASI. So usually in the clay type of soil, this NC value will be 9. So this NC value you should take it as 9. So 9. And this alpha and these parameters is nothing but alpha. What is alpha? Alpha is nothing but the reduction factor or adhesion factor depending on the consistency of your cohesive strata. So these values anyway you will get it from the IS 2911. This alpha value and the K value and this NQ value. Anyway, NC you should remember this. Okay, so it's a simple number. Okay, 9 you should remember. Like in your shallow foundations, NC was like 5.7 something. No, it was 5.7. So like that in pile it is a 9. Okay. So any doubt here till now? Any doubts regarding the these static method? Okay, this is called the static method. Well, load carrying capacity with the by static method. Any doubts? No. Okay, then if you don't have any doubt, then I will stop it here. Okay, so then tomorrow we'll take the remaining class.